as well as Andrew West and John Bachansky, and an undergraduate working with me, Heather Gunning, who has a poster today, which you all should go see on A-delta variability. Or Emily can give you the wireless one.
Is there a wireless one here?
Yeah.
Oh yeah. Can we turn that one off? No, just stay away from it. Okay. I'll just sneak back for the button. Okay, so here when I talk about ultra-cool dwarfs, I'm talking about M7 to L3. I think it's a really interesting set of ultra-cool dwarfs, in part because often people who work with M dwarfs, they try to get the largest samples possible, which is, of course, around M3, M4, M5. People who work with L dwarfs are often trying to get the later L dwarfs. They're trying to find the ones that are brown dwarfs. So I think this is, in some ways, an unprobed population of stars and brown dwarfs. And that's one of the other interesting things about it. Here I'm showing the Burroughs models, which are tracks of constant mass, and how they evolve in luminosity as a function of time. Along the right side, there's a really rough conversion to spectral type, just to give you an idea. And the masses are in color on the side. And the point that I want to make is that there are both brown dwarfs and stars in the M7 through L4 or through L3 bins, even at disk ages. All the evolution doesn't happen when stars are in young clusters or brown dwarfs are in young clusters. So even in the disk, we're looking at a population that includes brown dwarfs that are younger than the stars around them. So kinematics can be a really interesting way to get a handle on which objects are stars and which objects are brown dwarfs. So kinematics, in case you need a refresher, or if you don't, I'm still going to tell you that kinematics are useful as an age indicator because the velocity dispersion and mean galactic height increases as stellar population ages. So this is because as stars orbit in the galactic potential, they have increasing numbers of interactions with molecular clouds in the plane of the galaxy. Each of these interactions is stochastic, so they're likely to puff the star up in height, and they're likely to put the velocity in a random direction, thus increasing its dispersion. And one point that I think is important to make here is that this effect is independent of the mass of the star or the brown dwarf. So solar-type stars respond to this in the same way that brown dwarfs do. So kinematics are a really valuable way to take what we know about the galaxy and apply it to brown dwarfs and stars. Ultra-cool dwarfs. So the question that I want to ask is which properties of M7 to L3 dwarfs correlate well with age? And I mean this empirically. We know that an older star is more likely to be metal poor. We know that it's less likely to be active. But when we look at the colors, when we look at the spectra, what are the exact correlations between these properties and age? So onto the sample. Today I'll be talking about my sample of stars from the Sloan Digital Sky Survey. It's a combination of two samples, or three, and the first one I'm going to talk about is from the Sloan Digital Sky Survey 1 and 2. So this survey ran from 2000 to 2008, covered approximately a quarter of the sky with UGRS photometry and optical spectroscopy. And this is just showing the print of it on the sky, mostly through the northern galactic pole. Within the survey, we and people in this room mostly have found 15 million M dwarfs with photometry, staggering number, 70,000 M dwarfs with spectroscopy, and 500 L dwarfs with spectroscopy. Now the M dwarf numbers are staggering just in themselves, but the L dwarfs, it's actually a really large number compared to the known L dwarfs. This represents about 70% of the known L dwarfs. So lots of objects from Sloan. For the ultra-cool dwarfs themselves, this shows the combination of the West et al. And my sample of L dwarfs in the M7 L3 range. There's about 10,000 of them. But I said that I was going to specifically talk about kinematics. When we look at objects that had published UVW velocities, there's actually a lot fewer late M dwarfs than there are with L dwarfs. This is because each spectrum had to have, well, each object had to have photometric distance, which is not very hard, most of them have those. A radial velocity from SDSS spectra, that's also relatively easy to measure. The survey spectra are really well calibrated. And then the M dwarfs all had USNO proper motions. It's an important difference here because USNO is correlated with the DSS plates, and you have to be a really bright nearby M dwarf to have a proper motion in that catalog. For the L dwarfs, I measured proper motions from SDSS and 2-mass positions, just simply looking for matches in both catalogs, measuring their difference. So the first thing I did when I wanted more M dwarfs was I've cross-correlated the SDSS and 2-mass positions, not cross-correlated, cross-matched the two catalogs, found proper motions for an extra 6,000 late M dwarfs. So that's a really pretty large sample, but I wanted to get more. That brings us to SDSS-3, the ongoing component of the Sloan Digital Sky Survey. The main difference between SDSS-3 and SDSS-1 and 2 is that there's no longer any photometric observations. It's all spectra. And the spectra which I find most useful, red optical spectra, is the Baryon Oscillation Sky Survey. Its main goal is to measure some parameter of large-scale structure or whatever. What's really important is that it has about 1,000 spectroscopic fibers per pointing per observation. The old Sloan had 600, so we're increasing the number of spectra per pointing. And even more important to us is that there are about 30 ancillary programs accepted to fill spare fibers. And our program, which I'm the PI of, was awarded 10,000 fibers to obtain spectra for late M and L dwarfs, which is a really large number of spectra, which is great. And I just wanted to mention here that I'm also looking at serendipitous M and L dwarfs, the ones that they thought were like quasars or red galaxies, and also some objects from other people's ancillary programs, if they happen to be looking at M dwarfs. So when we add these in, we've spectral typed and analyzed about a little over 1,000 M dwarfs that have UVW kinematics. It's actually more like 3,000, but we weren't able to measure proper motions for all of them. I had help with the spectral typing. All of them were by eye from my undergraduate collaborator, Heather. And I wanted to also mention that the BOSS spectra aren't complete. The survey runs from 2008 to 2014. So we have 1,000 now, and what I was trying to demonstrate here, little pointer, all the purple dots and the blue dots are the DR7, the SDSS 1 and 2. The green dots here are BOSS spectra, and they don't cover the whole footprint yet. So when BOSS targets this area, we're going to get a lot more spectra. So we have about 1,000 now. I expect something more like 3,000 to 4,000 with UVW kinematics in the spectral type range. So that'll be really exciting. For now, this is pretty exciting, I think. 8,000 ultra-cool dwarfs with UVW kinematics. Okay, so the first thing I wanted to look at is activity and age. So this is fraction of active stars per absolute vertical distance from the plane, from the DR7 M dwarf sample. And they're split into spectral types, M2, M3, M4, M5, M6, and 7. And what I'm interested in, basically in general, is taking everything we found for M dwarfs, seeing if it applies to ultra-cool dwarfs, seeing if we can take that and apply that to even later dwarfs. So here's a fraction with H-alpha emission, or activity fraction, versus absolute distance from the galactic plane. For M7 dwarfs, we see a similar curve to what Andrew and everyone found. And then for M8 dwarfs, also a decrease. For M9 dwarfs, also a decrease. This is just with a small increase in the number. But one of the really interesting things, I think, okay, L dwarfs, you can't really see them further than about 100 parsecs. You need a really big telescope to get even a little data. So if we use kinematics, we can look at the same sort of correlation without needing to look so far. So this is M7, M8, M9, and L0, splitting up the active and inactive stars in each spectral type bin and comparing their velocity dispersions. So the active stars tend to have lower velocity dispersions than the inactive stars. And I just wanted to note that I'm showing the UV and W velocity dispersions here. You should be comparing the U to the U, the V to the V, and the W to the W. They're necessarily going to be different. So M7s, inactive, slow movers, young. Active, slow movers, young. Inactive, wider velocity dispersion, older stars. And we can even see this for the L0 dwarfs. It's not as strong a correlation, but we also have smaller numbers of them to begin with. So kinematics are a really good way to get a handle on which of the trends that we can see for M dwarfs apply for L dwarfs as well. So another thing that I've started at the beginning is talking about how many brown dwarfs are included in each spectral type bin. So there should be more young brown dwarfs that have an L3 spectral type than M7. So we're thinking that, oh, it should be that M dwarfs have larger velocity dispersions than L dwarfs. And we do actually see that with the sample. I wouldn't call it an extremely strong trend, but it's certainly suggestive. And I'd also like to note these error bars are statistical, formal errors. We do expect the actual errors to be a little bigger. Starting to see some correlations there. With kinematics, though, I think we can apply the fact that we can see some of these younger brown dwarfs and distinguish them in velocities and use this to look at more properties. Okay, so on to colors. So here, 4 different plots of R minus Z, I minus Z, I minus J, and J minus K as a function of spectral type. This may be a little more complicated than it needs to be, but I have single objects here in this sort of muddy green line. The median for each spectral type bin is the black here, and then these are the standard deviations from the median. So if you see a dark, the dark is the 1 sigma standard deviation. So in I minus C and I minus J, these colors are really spectral type dependent. They're really good tracers of effective temperature through these spectral type bins. In J minus K especially, but somewhat R minus Z for these spectral types, it seems that effective temperature isn't the primary indicator of whether a color is going to be, of what the object's color is going to be. So one of the things that I want to do is look at the kinematics and see if there's a correlation with age. This has been done already with J minus K color for the L dwarfs. This is a plot from the Brown Dwarfs Kinematic Project Proper Motion Survey by Jackie. And you can see that this is a tangential velocity as a function of J minus K color, split into the blue and the red L dwarfs. And the blue objects have a wider velocity dispersion than the red objects, showing that the bluer L dwarfs are older than the red ones. I looked at this also with my L dwarf sample from SDSS. Instead of just color, this is sort of a color dispersion measurement. So these are bluer objects and these are redder objects. And I've plotted velocity dispersion in UV and W. And there is a correlation. The bluer objects have wider velocity dispersions than the redder objects. So the bluer ones are older than the redder ones. So then I also wanted to look at this for different colors for the M dwarfs. So I've got R minus C, I minus C, I minus J, and Z minus H, looking for correlations between colors and kinematics. So we do see a very slight trend that the velocity dispersion of the bluer objects in many of these bands are slightly higher than the redder ones. This is probably a metallicity effect because metals tend to have more bands than the blue. Bluer objects do tend to be more metal poor. Wait, yes. Okay. All right, so I'm going to move on to the conclusions. One thing that I definitely want to take away is that BOSS is observing many late M and L dwarfs. We've already got a large sample and we're going to get more. The age-activity relation can be extended to L dwarfs, at least somewhat, and hopefully with more data we'll be able to look at that in more detail. And that colors and kinematics are an excellent tool for finding age and metallicity diagnostics, and I think will be even more useful in the future. And that's it.